Assalamu alaikum. I am Arud Suleiman and my topic of presentation is electric textile. First of all, it's include table of content, which includes abstract, introduction, material and method, variable computing, manufacturing of electronic textiles, chemistry of electric system, early research, textile sensors, e-textile sensing antenna, e-textile application strength, fabric coloration system, color changing fabric with electronic system, conclusion and at last references. First of all, abstract. Textile has been at the heart of human technological progress for the thousands of years, with textile developments closely tied to key inventions that have shaped societies. The relatively recent invention of electronic textile is set to push boundaries again and has already opened up the potential for garment relevant to defense, sports, medicine, and health monitoring. The aim of this review is to provide an overview of the key innovative pathway in the development of electronic textile to date, using source available in the public domain regarding electronic textile, which is called e-textile. This includes academic literature, commercialized products, and published patents. The literature shows that electronics can be integrated into textile, where integration is achieved by either attaching the electronics onto the surface of a textile. Electronics are added at the textile manufacturing stage, or electronic are incorporated at the yarn stage. Introduction. Usually textiles are defined as smart when they can respond to changes of environmental parameter, for example by changing their color due to ultraviolet radiation, or by measuring vital signs and sending them to smartphone to enable the investigation of one's fitness level. In many cases, such smart functionalities are based on electronic components. Define them as electronic textile or e-textile. Such e-textile usually contain sensors, actuators, internal or external communications, a power source, and finally a data processes. Many of these parts were only made available during the last decades by inventions such as conductive polymers or transistors, often based on one or two fine metal wires coated by an organic semiconductor. Other parts, such as the data processor, cannot be transferred into textile structures, but due to steady miniaturization are more and more able to be integrated into textile structures. Many other electronic parts made their way from being added to textile by seeing to integration on the fabric level, and more recently even on the yarn or fiber level. Nowadays, diverse level of textile integration can be found in e-textile, from wearable computers with openly visible electronics using textiles only to make the electronics wearable, to fully integrated electronic functionalities. Electronic textile are simply e-textile are textiles with embedded electronics and some fiber material possessing electrical characteristics and providing some useful function. An electronic textile is a fabric that conduct electricity. If it is combined with electronic components, it can sense changes in its environment and respond by giving off light, sound, or radio waves. Electronic textile allows little bit of computation to occur on the body. They usually contain conductive yarns that are either spun or twisted and incorporate some amount of conductive material such as strands of silver or stainless steel to enable electrical conductivity. E-textile, also known as electronic textile or smart textile, are fabrics that enable digital components including small computer and electronics to be embedded in them. Next includes material and method. First of all, material and variable computing. Variable computing is a type of variable that contains information technology and is able to store, manipulate, or transmit data. The inclusion of variable computing is what makes an e-textile a smart textile. The 1990s and early 2000s saw patents for devices either integrated onto to the surface of garments are contained within pockets beginning to emerge. These are generally regarded as first generation e-textile, where an electrical circuit or electronic component were attached to a garment. The initial commercialized first generation e-textile garment began to appear on the market with industrial clothing division plus jackets in 2000. This jacket attached electronic devices into pockets. An important component towards the successful development of wearable computing included methods of creating electronic circuits within textiles. Another patent describes using electrically insulating and electrically conductive yarn woven into a garment to create an electronic circuit. A later patent further built on the use of knitting techniques to create electrical circuit and pathways. In 2006, it was described that an in-depth mean of forming electrical circuits within textile structure. An e-textile patent published in 2006 discussed the inclusion of devices such as Bluetooth and electrical connection required between components, with the concept of wearable computing existing for a number of years. In 2006, Force and Sullivan provided an excellent review of wearable computing at that time. A variety of other developments linked to a wearable computing appeared in the 2000s. Some recent development in wearable computing have veered away from the textile, including the Google Glass. Despite these devices being wearable and not textiles, textile computing has still made significant strides in recent years. Graphene technology may be a key contributor to further development of wearable computing. The U.S. Army Research Laboratory discussed the potential of graphene-based nanoelectronics for application in wearable electronics in a report produced in 2012. Interfacing with e-textile is also of importance for further development. A recent Microsoft patent described an interface system for using muscle movement to control a computer or other device. The use of organic conductive polymers may also improve the potential for wearable computing. One of the scientists have also developed a fiber-level electrochemical. Manufacturing of electronic textile, a thread can be made to conduct electricity by either coating it with metal like copper or silver. It can be made conductive by combining cotton and nylon fibers with metal fibers when it is spun. Input for electronic textiles to obtain information from wearable devices. Components such as sensors are often used. For instance, environmental sensors, antennas, global positioning system, GPS receivers, sound sensors, and cameras. Such sensors can be divided on active and passive ways. Active inputs are controlled by a user through a tactile or acoustic feedback system, which provide an intuitive interaction with the garment. Passive inputs collect biometric data from the human body as well as data through wireless transmission system. Then next is construction of electronic textiles. Conductive fabrics and textile are plated or woven with metallic elements such as silver, nickel, tin, copper, and aluminium. These are electro-nylon, nickel, clear mesh, soft mesh, lycra, and steel cloth. All these textiles show amazing electrical properties with low surface resistance, which can be used for making flexible and soft electrical circuits within garment and other products. Pressure and position sensing systems are also available. They are light weight, flexible, durable, soft, and washable, and can be sewn like traditional textiles, which make them a great replacement for wires in computational garments. Conductive threads and yarns have similar purpose to wear, and that is to create conductive path from one point to another. However, unlike the wires, they are flexible and can be sewn, woven, or embroidered onto textile, allowing for soft circuits to be created. Conductive threads and yarn offer alternative ways of connecting electronics on soft and flexible textile mediums, as well as offering traditional textile manufacturing techniques for creating computational garments. Conductive coating. Conductive coatings are used to convert traditional textile into electrical conductive material. The coating can be applied to different types of traditional fibers, yarns, and fabrics without changing their flexibility, density, and handling. Conductive ink is an ink that conducts electricity, providing new way of printing and drying circuits. This special ink can be applied to textiles and other substrates. Conductive ink contain powered metals such as carbon, copper, or silver mixed with traditional inks. Other materials are which can be used are shape memory alloys, which are also called SMA, or muscle wires, piezoelectric material, chromic material, which is color material, photochromic, thermochromic inks, and nanomaterials and microfibers. Nanotechnology has also been applied. Chemistry of next is chemistry of electric system. E-textile are a collection of fabrication methods that use conductive thread or textile to form electrical circuit. We will expand our interest in e-textile here to include circuitry built with traditional electrical components that are mounted on a textile substrate. E-textiles may be used for variable application, but as will be explored, they are also chosen for audio application and devices that are not worn on the body. Textile based electronic components have gained interest in the field of science and technology. Recent developments in nanotechnology have enabled the integration of electronic components into textiles while retaining desirable characteristics such as their flexibility, strength, and conductivity. Various materials were investigated in detail to obtain current conductive textile technology, and the integration of electronic components into these textiles shown great promise for common everyday applications. The harvest and the storage of energy in textile electronics is a challenge that requires further attention in order to enable complete adoption of this technology in practical implementation. Early research. E-textile emerged from wearable technology research communities which were largely focused on medical and military application. And the MIT Medical Lab was a significant hub of research on wearable computers, while some students were working on systems that would be predecessors to Google Glass. Other in the lab started looking at integrating computations directly into conductive textile. Post and Orth are credited with producing the first published research on e-textile. As part of their research, they developed a series of prototype systems exploring various interactions and outputs, with music generation as one of the first use cases. Their MIDE jacket was a denim jacket with touch-sensitive embroidery which controlled and embedded MIDE synthesizers. Other projects worked with similar technology, integrating multiple pressure sensors into squeezable ball designed for musical performances. Textile sensors. The conductive material are necessary in all e-textiles. However, diverse other material, for example semiconductors, have to be added for different purposes. Usually many materials are combined, for example in the form of subsequent coating layers on textile fabrics or around yarns or fibers. Here some examples for textile integrated sensors are described. Give an overview of which sensors can already be produced based on textile fabrics, yarns, or fibers, beside the already existing possibility of integrating small rigid sensor into fabric or yarn. The simplest sensors are based on pure conductive yarn or layer with different shapes and function. Embedding silver nanoparticles in a stretchable fiber enable the producing of a durable strain sensor with a large sensing range, which was used in a glove to control a robot hand. The integration of a strain sensor from carbon black is a thermoplastic elastomer was used to prepare a body posture registering shirt. In this first figure, it is a sensor thread integrated in a prototype body posture recognition, and B is a sensor position. Fiber coated with carbon nanotubes were found to be suitable temperature sensors since their resistance was nearly unchanged by the repeating bending of fibers as opposed to conductive carbon coating. A carbon nanotube screen printed electrode array was sandwiched between a lactic fabric and nylon fabric to form a triboelectric nanogenerator, which was found to be washable and could be used as a self-powered touch sensor or gesture sensor for human-machine interaction. ECG measurement can be performed using different conductive textile as electrodes. Even an ammonia sensor was produced by a gold or carbon nanotube or gold structures, with the carbon nanotubes being coated on a cotton yarn based on the ammonia being a strong reducing agent, and thus eliminating the majority of holes in the carbon nanotubes, which resulted in a decrease in resistivity. Polypyrrole and other several other conductive polymer can be used. More parameters can be detected by combining part with different physical properties. In the simplest form, a parallel plate capacitor can be created by sandwiching a non-conductive textile or compressive foam with two conductive textile layers. For example, polyvinylidene fluoride, which is abbreviated as PVDF, has piezoelectric and pyroelectric properties. That is, it responds also to temperature changes by producing an electric charge. The latter can be used for the detection of the presence of a human, but has also been developed further for use in the heartbeat and respiratory signal detection. Piezoelectric material like polyvinylidene fluoride can generally not only be used as a sensor but can even be harvest electrical energy when the piezoelectric textile are compressed or bent. Lactate and glucose sensor were prepared by electrochemical deposition of platinum nanospheres on nitrogen doped carbonized silk and drop casting of a lactate oxidase or glucose oxidase or chitosan solution on these platinum or silk electrodes. Sensors of sodium and potassium ions were produced by adding ion selective membrane. Ascorbic acid and uric acid as typical health related biomarker molecules were directly detected using the carbonized silk working electrode. The figure below depict some of the sensor responses showing the desired selectivity of the sensors. These are the graph which are generated between current and the time. Generally, diverse physical and chemical sensors can be prepared by combining conductive material with other materials such as semiconductors, dielectrics, non-conductive spaces, etc., as long as coating them on flexible open pore textile substrate is possible and the necessary material are non-toxic. Textronics has developed an electrotextile sensor that can be incorporated into clothing. The sensor captures the wearer heart rate. The Textronics use the philosophy that the garment must work well as a garment as well as a piece of technology. Three types of textile pressure sensors are known. One is resistive, other is capacitive, and last one is piezoresistive. Resistive measurement is based on the material geometric strain which cause increasing of the resistivity of a conductive path. In piezoresistive sensors are used nickel or platinum alloys where two effects are added and resistivity is growing up to more than 3 times as large due to geometry effects alone. Capacitance measurement are as simple as resistive measurement and also power consuming with a high accuracy. Bicapacitive sensor, a deformable insulating layer is used which separates the two conductive layers. By applying of a force, the distance between the two conductive layers is changed, which results in a change of the electrical field between the electrodes and therefore in a change of the capacity of the sensor. The measurement of these two physical quantities require different electronic components. E-textile sensing antenna. To realize an e-textile sensing antenna for vital sign monitoring, the antenna needs to maintain its operation in proximity with the human body. This is evaluated through the antenna radiation efficiency and reflection coefficient, where a sufficiently low reflection under 10% indicates that the antenna is suitable for integration with different transmitters. Furthermore, as the antenna is low profile and does not require a specific substrate thickness to radiate efficiently, the selective design is suitable for implementation on different textile substrate. This figure shows the layout and the photograph of the antenna respectively. The proposed e-textile sensing antenna is shown in the figure. E-textile applications. There are several applications of e-textile ranging from healthcare to consumer goods. Here are few very we feel play an important role in advancing technology across the industries. First application is health monitoring. Perhaps the most well researched application of e-textile is medical, specifically the monitoring of health condition. Currently there are medical variables that have been invented to monitor several aspects of a person's health, such as blood pressure, heart rate, and symptom of diseases. For example, high blood pressure. Several governments have been made with biosensors to collect data on systolic and diastolic blood pressure. This allows the user to easily detect triggers as they go about their days and report back to their physician, so an effective treatment and management can be made. Next application is worker safety. Occupational safety is another area where e-textile can provide a great deal of service. One hypothetical use is for construction workers who are working outdoor late at night. LED lights can be affixed to a uniform and automatically turn on when it gets dark outside, improving visibility. However, LEDs are not the only electronic component used for safety application. There are a lot of other safety applications. Next application is comfortable driving. A favorable feature among driver is heated seats. Who does not like being blanketed in a warmth while driving? While it is often a luxury, heated seats and wheels are essential for drivers in freezed temperature. Turn out that you can thank e-textile for this technology. Next application is athletic performance. Several companies are developing garments and accessories made from smart textile that track and record data based on athletes' motion. Reticence, for example, developed a smart insole for runners to place in their sneakers. The smart insole can help runners improve their form and avoid injury. This invention could prove useful to marathon runners when they are in the midst of training and looking for ways to improve their overall performance. When it comes to clothing, companies like Wearable Experiments and Athos have led the way for the high performing athletic wears that bring extra functionality to athletes. Next application is new user interface. E-textile can also be used to get the most out of external devices and media. jQuery by Google is a perfect example of this. Jacquard is a wearable technology created by Google that have been added to garment and accessories. The capacitive touch grid that act as a user interface on the jacket is woven directly into the product and has the ability to answer calls, play music, take photos, and get direction with a simple gesture. And e-textile are just making it easier to use device. They are saving battery power. A fabric property is a characteristic of a material which it should possess for it to be used in a desired application satisfactorily. In other words, it can also be termed as a requirement of a textile material for certain purpose. Some other properties of fabric garments required in the performance apparel. These are the some properties which required for the good e-textile. Absorb moisture readily, appearance attractive, bend repeatedly without breaking, conceal or protect, dimensionally stable, easy to dispose, easy to maintain. Fabric hangs freely, good surface texture, impact protection, luster, non-absorbent, protect the body, resilient, resistance to insect damage, resistance to mild dew, shrinkage resistance, soft next to skin, transfer electric charge, transfer or maintain heat, withstand pulling force. Strength about tearing strength of fabric. Tear strength is most important in the assessment of serviceability of the fabric. In order to tear a cloth, the threads are broken singly. It is therefore a frequent mode of fabric failure. The factor which contribute to the resistance to tear is: first is strength of the yarn. Normal to tear. Suppose you are trying to tear the weft yarn, then those yarn need to be stronger. Freedom of movement of the yarn in the direction of tear, as in the freedom of movement in the warp yarn should be there, which can be done by reducing EPI. There are two type of tear strength measurement come into play. First is the initial tear strength. It is when the load is applied on the fabric to tear it. This load is always higher than the average tear strength. It is because of the fact that up to this load, yarn crimp removal and sliding takes place. But once this point is reached, and the load is instantly transferred to the successive yarn, and the tear strength obtained is known as the average tear strength. Fabric tensile strength characteristic refers to the pattern of mechanical deformation of the fabric when subjected to tensile forces along the wrap and weft direction. Commonly speaking, is a phenomenon in which a fabric is elongated and deformed, or even broken and damaged by the action of external force in tension. The tensile strength of a fabric can be influenced by the top three factors that are mentioned below. First factor is density of the fabric. Second is strength of the thread used in yarn, and variety and the quality of the fabric. These are the some properties of the fabric, which is durability, aesthetic, comfort, and maintenance. Fabric coloration system. Dyeing is a process of thorough coloration of the textile, and its success lies on the type and the extent of pre-treatment imparted to develop good absorbency as well as whiteness. Where various influencing factors during dyeing, such as pH, form of textile, type of fiber, formulation of dyeing recipe, preparation of dyeing solution, liquor ratio, selection of machinery, etc., play a crucial role in the development of leveled shades with least effort and cost. Right programming of the dyeing schedule and scientific approaches for recipe formulation as well as addition, if required, are the other keys to avail maximum utilization of machineries, workforce, power, and finally delivery of the product to the market at the right time. Researchers at the University of Central Florida has developed a color-changing fabric that can be controlled with a smartphone. The technology is currently being applied to prototypes for products such as backpacks and purses. The technology uses a series of microwires that are weaved into the clothing along with the battery pack. When electrical current flows through the wires, the temperature of the thread is raised. As a result, special pigments in the thread are able to change their colors. This new technology is different from the previous color changing fabrics on the market that rely on the light emitting diodes LEDs. Beyond controlling a fabric color, users changes what pattern appear on the fabric from their smartphones. For example, a user can gradually add blue stripes to a solid color tote bag by pressing a stripe button on the smartphone or computer. As of now, the university's team is making the product in Melbourne, Florida, with collaborators at the Hills, and the team is working to create thinner fabrics that could be applied to apparel such as t-shirts. In the future, researchers think the color changing fabrics can have medical and military application. Ultimately, the patent pending fabrics has the ability to be used across a broad range of application, from clothing and accessories to furniture and fixed installation in housing and business decors. At last, conclusion and prospects. Electronic textile can be used for a broad range of application, from health monitoring and monitoring the vital signs of athletes to soft robotics, and from gas sensors to piezo resistive sensors monitoring wind blades. Generally, since we are human, are normally surrounded by textiles, most applications of e-textile are related to humans, supporting us in different situations, making the use of electronic devices easier by integrating them fully or partly into garments, or just adding new functionalities due to design aspects. It should not be forgotten that deeper electronic functions are integrated into textile, the more challenging the development is, since experience from rigid electronics can uh, only partly be transferred. Nevertheless, the research and development of electronic textiles are steadily advancing so that new functionalities can regularly be expected to become available, making electronic textile more and more useful in our daily life. These are the references which from which I get data. Thank you. That's all from my side.